Hey everybody, today we're going to talk a little bit about modeling some problems with quadratic equations. And there's going to be two types that I'm really going to focus on for you guys, and that's going to be an area model and then a vertical motion model. And we're going to do a little bit more with the vertical motion model a little bit later, but just kind of show you guys what they look like, how we can actually write some functions that can model some real world situations. So the first one we've dealt with a little bit already. We worked with it a little bit last unit. But let's say I have some sort of rectangle that I want to find the area of, and I know that this side is x plus 7, and I know that this side is x plus 3, right? So if I want to find the area of a rectangle, I know that's length times width. And in this case, we're going to multiply two binomials by each other. So we're going to go back and how do you multiply binomials by each other, right? We got to distribute. So if I wanted to find the area of this thing, I'm going to do x plus 7 times x plus 3. X times x is x squared. X times 3 is just 3x. 7 times x is 7x, and 7 times 3 is 21. And then, of course, we're going to add our like terms in here. So we got x squared plus 10x plus 21. Now, that's the function that represents the area of this, right? So we'll say f of x equals. But what if I wanted to plug in a specific number now? So for example, what if x was 5? Well, if x was 5, this side would really be 12, and this side, you can't see that, can you? This side would really be 12, this side would really be 8, and we could multiply 8 times 12 and get 96. But instead of doing it that way, let's use our model, our function, and let's just plug in f of 5. So I can plug 5 in here to our function and get 5 squared plus 10 times 5 plus 21, right? So 5 squared is 25. 10 times 5 is 50 plus 21. And if you add all of those lovely numbers together, 25, 75, 80, 96, is exactly what we would have got from just the picture model, right? So it's really cool. That will actually always work. Once we multiply our binomials together and we get this quadratic function, I can plug in any number I want for x, and it's going to spit out what the actual area of this model would be. So you can see the application there, right? Maybe I'm not sure how big I want to build this thing. And I can just I just know that this side I want to be 7 longer than some number, and this side 3 longer than the same number. So this side's always 4 longer than this side, really, right? And then I can just use this quadratic model, plug in whatever I want, until I can find the area that I am most comfortable with. So that's super cool. And most area models are going to work pretty much the same way as that. I think you guys will be okay with that. Now, vertical motion, that's going to be a little bit newer. So, vertical motion, or I remember calling these projectile motion when I was in school. But the base formula is going to look something like this. H of, oh, that's an F. Hang on. H of t equals negative 16t squared plus v sub o t plus h sub o. All right. So, probably wondering, what is this alphabet soup that you just wrote on the board, Oatster, right? So let's talk a little bit. This negative 16 that's in front of the t squared term, our a value, if you will, is actually the constant for gravity. And that's why these vertical motion problems are always going to have this negative 16 in there, unless you're doing one in outer space or something like that. But on the planet Earth, every time that we throw something up, it comes back down at the same constant, because that's how gravity works, right? So that negative 16 represents that number. This v sub o is initial velocity. So how fast did you throw this thing into the air? Was it shot from a cannon or from a gun? Or maybe you just shot it like a basketball, right? Anything that moves vertically, that has some sort of initial velocity is going to go here. It is worth noting that if you drop something, just pick it up and drop it, it doesn't have an initial velocity. So my initial velocity would be 0. So if it was just completely still and then it started moving, we're not going to have an initial velocity. However, this h sub o, our constant term, is going to be our initial height. How high was this thing when you let it go, when you threw it, when you shot it, right? Maybe it was 6 foot, right? If it's a basketball, maybe it's like 7 foot for me. Maybe you were on top of a building and you threw something off. In that case, however high you are. This number is going to tell us our initial value of height, how tall was something. So that's like the basic model. So maybe it'll say something like Pete threw a ball off of a 10-foot ladder at a velocity. And I think usually with those velocities, it just depends, but usually we're talking feet per second. 12 feet per second. Right, something like this. So we have this ball, this kid's throwing the ball. We know everything that we need to know here. So we can model it using our base formula. So h sub t is going to be negative 16t squared, that part's always the same, plus my initial velocity is 12 feet per second, so it's going to be 12t, plus my initial height is 10 feet, because that's the top of the ladder I'm throwing the ball, right? So my model might look something like that. Absolutely, that definitely could work. So we can model the flight path of this ball going, and you think about the reason why it's a quadratic, think about what the path of this ball is going to look like, right? I'm at a ladder, 10 feet up, I throw it, it comes back down, right? It's definitely a parabola. There's this arc, there's a certain point where it can't get any higher, the vertex, and then it starts to fall the same way that it went up, right? Think of a football. It has that nice curve as Baker Mayfield throws it 60 yards, right? So here's kind of the idea, how we're going to get this. Now we can say things like, how high is the ball after 2 seconds? So after 2 seconds, I can plug in 2 everywhere. Then I see a T, and I can figure out how high the ball actually is going to be. 2 squared is 4. 4 times negative 16 is negative 64. 12 times 2 is 24. And plus 10. 2 is a bad choice because it looks like it's going to be underground, right? It's already going to hit the ground. Negative 64 plus 34 would be negative 30 feet. So maybe if it went into a cave or something, I guess that could work. But typically, that was just a bad choice for me. It's already going to be at the ground. Because I guess 10 feet, obviously, is not very high in the air. Yeah, that was probably dumb. But let's do 1 instead. Just so you can see one that will kind of make sense for you. I think it'll still be in the air after 1 second. I guess we'll find out, right? So negative 16, 1 squared is 1 times negative 16 is negative 16. 12 times 1 is 12 plus 10. So negative 4, 6. So after 1 second, it's going to be 6 feet off the ground. So it's still going to have a little bit of height, but then obviously it's going to fall pretty quickly. And that's kind of the vertical motion problems. So right now we're only going to worry about modeling with them. And then we can actually put some real world data behind it and start solving some cool problems. So when we start solving in Unit 9, we'll kind of come back here and visit these again. All right? Cool. That should be a decent amount of info. There's a couple problems for homework, not too many, so you can try those out. Later.